Good. Welcome to the lecture on programming, data analysis, and deep learning in Python. Last week, we implemented this small program to check whether a list is a palindrome, and we fixed one bug. Did anybody in the meanwhile, in the last week, find further bugs in this program? Okay, it seems not. So let's try to see whether it's now fixed. So we're checking a palindrome with 2 letters. Let's say A, oops. Oh, name debug is not defined. Okay, I should probably re-execute this thing here. I hope that's sufficient. Okay. So we have a list AB, which clearly is not a palindrome, and our code still says it's a palindrome. So apparently there's some bug left in our code. And as we go on, I will become a bit lazy of always testing the code manually, right? And probably that's the case for you too. If you're debugging something, and you always have to enter manual tests into your code, that becomes very boring. Especially if you work on some big piece of software, what you probably want to do is you want to automate the testing. So you want to write a new program where the only purpose of that new program is to test your program. So it's an automated tester. You want to implement a small robot that tests your program. And that testing robot, we usually call a test harness. Let's write a small function which can do that. Def test harness. And the only purpose of this function will be to test our palindrome tester. And in the test harness, you usually when you test your program, you will always test it on some test cases. Most of the time, you cannot test all possible cases, but you will try to find some representative cases where you can test your program on. So let's test 2 cases, one which is not a palindrome and another one which is a palindrome. So maybe our test case 1 will be a list with just the numbers 1 and 2, which is not a palindrome. So now we will call our function. Result is ispal. I think the function was called ispal. Yeah, the function is ispal. Test case 1. And then debug. Maybe just convert that to a string. Case 1 plus string of result. Maybe we want a small spacer in the middle. Okay, so this will be our test case 1. And then let's implement a second test case. So our test case 2 should be one which is a palindrome. So we just add a 1 here. And okay, so this code, all this code does is that it uses these 2 test cases, one with the list 1, 2, and one with the list 1 to 1, and it tests our program on these 2 test cases. Then let's call our test harness. Okay, so 1, 2 is a palindrome. Okay, that's not right. 1 to 1 is really a palindrome. That's okay. So there's still some bug left in the program, especially in the case where things are not palindromes and our code still says it's a palindrome. If you're searching for bugs, one good strategy is usually binary search. So if this is your program and you cannot see the bug, but you suspect that the bug is somewhere between here and here, then often a good strategy is to add a debug message somewhere in the middle to check whether everything above it is correct. And then hopefully you know whether the code, the bug is above or below that. And if you think the bug is below that, then you add another debug message here. And then if you think the bug is above that, then you add another debug message here. And by this, you can get closer to your bug. Okay, so let's go to our ispell method. So this is a method that has a bug. And let's add some debug messages. Probably here. Let's see whether the reverse works. Debug, let's just print x. Let's print x of x, and maybe let's also print temp. Temp is this. Okay, and then let's call our test harness again. Okay, so x is 1, 2. That's okay, that's my input. But then temp should be reversed. So temp is still 1, 2. So it did not get reversed. Well, there is a problem somewhere. And temp doesn't reverse our input. Maybe we can see whether this code works. Let's do some list manually. So now you can take some of your code and execute that manually. So L is 1, 2, and then I say L dot reverse. Oh, that doesn't give me any output. Does anybody see a problem in this piece of code here? Yes?
Maybe we have to assign L to L dot reverse with brackets, so it's
Okay, yeah. So what L dot reverse does, it gives us a method, but it does not execute the method, right? So the return value of L dot reverse is this function, but it doesn't execute the function. So if we want to execute the function, we have to add these parentheses. There's no return value, but now L got reversed. Okay, so we found the problem. Let's now go here, copy that here, and fix the problem. Okay, and then let's call our test harness again. So hopefully now everything works fine. Okay, so this still says that 2, 1 is a palindrome. So now temp got reversed, but x got reversed too. Let's maybe look here. So now temp got reversed, but x got reversed too. So maybe one thing that we can do is we can, let's print, maybe what we should do is, we could add more temp messages here. So maybe we can print, why did x get reversed? So, does anybody see why x got reversed? Maybe just by eyeballing it. So what we could do is we could add more debug messages if we are not sure what's going on. But maybe somebody can see the problem. Yes?
Maybe we have to copy the x?
Yeah. So let's print our favorite. Let's draw our favorite graphic. So if we look at the refs, the references and the objects. Then we have the local scope. We have the local variable x, which points to our lists. And then we create a new variable temp, which we make point to the same list. And now we reverse temp. So we reverse this list. And obviously now x also got reversed, right? So that was exactly, that was a good idea. Let's not make, so instead of making temp point to the same list, the idea is now that we copy that list. So we have this list twice. So what we actually want is to not make temp point to the same list, but to copy the list, make temp point to the copied list, and now reverse the copied list. And this doesn't reverse the list on x. So we say temp is x.copy. Then we reverse temp. We don't reverse x, hopefully. Let's call our test harness again. So now x is 1, 2, temp is 2, 1. So temp got reversed, x did not get reversed. 1, 2 is not a palindrome. And here x is the same as x reversed. So 1, 2, 1 is a palindrome. So we found a number of bugs. I'm not sure whether there are any bugs left, but our test harness doesn't find any more bugs, right? So there can be two cases. Either there are no more bugs, or our test harness does not cover all cases, right? So you can never be sure that there's no bugs left in your program because your test harness can never cover all possible cases. Are there some questions for debugging? I don't say that you have to write a test harness for every small program, right? If you have a tiny program, probably you don't have to write a test harness. But as your program gets bigger, it may become very useful to write a test harness. And then a good strategy is to add debug messages. And it's also sometimes, especially later when we deal with matrices, it can be good to add a lot of assertions to make sure that all the shapes of the dimensions of the matrices are what you expect. More questions? Okay. So if there's no more questions for debugging, we are done with the introductory part of the lecture. So we are done with introducing Python. And what we will now do is we will do the more interesting stuff. And we will do actual interesting calculations with Python. So we will now start with NumPy, numerical Python, which is what you will want to use if you're doing any serious calculations with like big amounts of data or some like little bit more complex mathematical calculations. You will probably not want to do that in pure Python because that will be slow. And instead you will want to use NumPy if you're dealing with vectors and matrices and so on. Okay, now we can program. That's good. Let's open a new notebook. Who of you has ever dealt with a vector? Oh, that's good. Okay. Maybe there's somebody left who doesn't, so I will do a short introduction. So up to now, we've been calculating mostly with numbers. Individual numbers we also call scalars. But if you go out there in nature, numbers often don't come alone, right? Numbers often come in groups, like in pairs or in triples. For example, if we go out to the botanical garden and we find some flowers, and we look at the leaves of the flowers, and then the leaves have a certain length and a certain width. But they're kind of coupled, right? The length and the width of the leaf, they still belong to the same flower. So what we can do is we can put the length here and on the x-axis, and we can put the width of the leaf on the y-axis, and then we can plot. Maybe we find like 20 flowers, and each of the flower will be a little dot here, right? And we can either draw dots or we can draw arrows. That doesn't really matter. There's two ways to think about these vectors, either as an arrow from the origin to the point or just the point itself. Or we want to describe, maybe this is the botanical garden, and we want to describe where we found the flower. If we want to describe where the flower was, maybe we want to add a coordinate system. Maybe this is the origin of the botanical garden, somewhere in the center. And then maybe this is north and this is east. And then we want to say we found this flower here, and we have to say how many meters. Maybe we just split this in meters. Maybe one flower was here, one flower was here, one flower was here, one flower was here. So here the length and the width, they define a pair of numbers, and here the position in north-south and the position in east-west define a position of a flower. So what we can now do is we can write down the numbers for that. For example, maybe this flower is 12, the length is 12 and the width is 8. And maybe this flower, the length is 16 and the width is 3. So these are vectors, and the number of elements of a vector can be arbitrary, right? And vectors, there's two ways of looking at vectors. We can either write the numbers on top of each other, and we call these column vectors. So we write them in columns. But we can also write them, we can flatten them out and write them like this. And it basically doesn't matter. So we can also write them like this. And then we call them row vectors. Okay. If we want to do something with vectors in Python, we have to import NumPy. And what we usually say is we say import NumPy. And NumPy is quite long, so we write import NumPy as NP because it's shorter, just to say NP. And if we want to create a vector, vectors in NumPy are called ND array. So the data type is ND array. And what we will do is we will specify these vectors as a list of lists. So what we basically do is we look at the rows of these vectors. So this is a row, and this is a row. And we will do, each row will be a list. So this row is a list. And then the entire thing also is a list. Because later we can have a matrix which has multiple rows. So we need one pair of brackets for the matrix or vector. And then for each row, we will need another pair of brackets for specifying this row. So if we want to create these vectors, we say, or maybe let's start with different numbers. So maybe we have a vector v, and we create that vector, and we say numpy array, so create this vector. And then we have a list for the entire vector, and then a list for the first row, and the elements are 3 and 2. So now v is a vector. V is now the vector 3, 2. Sometimes we want, or most of the time, we want the vector not really lying down like this, like a row vector, but we want to have a column vector. We want it to stand up. And if we want to convert between lying down and standing up, what we do is we transpose it as a vector. So if we say 3, 2, transpose, we just do a small t up here. And what we do is we just look at this main diagonal and we flip it. So this is 3, 2. So we have our vector v, and we want it to be a column vector. So we say v equals v transpose. So we just say v dot t for transposing the vector. Maybe you want to look at that. V equals, oh, now I transported this twice, sorry. Okay. And now you see why I started entering the vector as a row vector, because if you define it as a column vector, you get a lot of brackets. If you define it as a column vector, you get one pair of brackets for the entire vector, and then for each row, so now as a column vector you have 2 rows, for each row you get another pair of brackets. Right. So you define the vector as a list of its rows. So what I recommend is to, if you have a longer vector, to always do a row vector first, because you type less brackets, and then just to transpose it to get the column vector. But basically they're the same vector. One is lying down, the other one is standing up. Maybe we want to define a second vector, w. W is np array. It's a vector 1, 3. And we transpose the thing to make it stand up. So this is now our vector w. So now we have the vectors, maybe I can draw that here. The first vector is 3, 2. This is v. And w is the vector 1, 3. We can draw them in a coordinate system. So v is 3 to the right, 1, 2, 3, and 2 up, 1, 2. So this is v. And w is 1 to the right and 3 up. So 1, 1, 2, 3. This is w. And the simplest thing we can do now is to add these two vectors. So what we can do now is we can say v plus w. And what we do is we just take all the elements and we add all the elements. So we just add them by elements. So this is 3, 2 plus 1, 3, which is 3 plus 1 is 4, and 2 plus 3 is 5. And visually what we do, if we add W to V, is we just add this number, add this vector, and we move it over here to the end of this vector, and we add it there. So let me get another color. So W was 1 to the right and 3 up. So from here, we go 1 to the right and 1, 2, 3. We go 1 to the right and 3 up. 1, 2, 3. So this is W. And now this entire vector is V plus W. So this is just V plus W. Okay, let's do that in Python. It's very simple. We just say V plus W as 4, 5. Just what we calculated on the blackboard. What we can also do is we can scale vectors. We can multiply them by numbers. For example, let's take this vector V. So V was 3, 2. So 2 times V is 2 times 3, 2. And then you just multiply each individual element. So this is 6, 4. And visually what you do is you just stretch this vector V, right? You just, so V was 1, 2, 3 to the right and 2 up. And if I stretch it to twice the length, I go 1, 2, 3 more to the right and 2 more up. So I just make it longer. So this is 2V. We can do that in Python. So we can just say 2 times V as the vector 6, 4. Then we can also subtract vectors. So if we want to calculate V minus W, one trick that we can do is we can just say this is the same as V plus negative 1 times W. Right? So we are back to vector addition. I think that's clear, right? That V minus W is V plus negative 1 times W. So this is V was 3, 2 plus negative 1 times W, 1, 3, which is 3, 2 plus negative 1, negative 3, which is 2, negative 1. Maybe I just replicate this image here. So V was 1, 2, 3 to the right and 2 up. So this was V. And W was 1 to the right and 1, 2, 3 up. So this was W. Now the first thing that I will do is I would calculate negative 1 times W, which is just flipping W through the origin. So minus W is 1, 2, 3 down and 1 to the left. So this is minus W. And V plus minus W is just adding this minus W vector to the end of V. So from here, I go 1, 2, 3 down and 1 to the left. So I add negative w here. And the resulting vector is 2 to the right and 1 down. So this is just v minus w. We can easily do that in Python. And we just say v minus w is the error to negative 1. Are there any questions so far? Yes?
So the vector is a list with one element of length, with one element which is also of length 2, and the transpose is a list of 2 elements with type lists. Is this correct?
So the vector is not really a list of lists. So this is just a visualization. In NumPy, the vector is a vector. So the vector is really something like this. And if you look inside NumPy, it's something that's optimized for performance. So it's a contiguous block of memory with some C code optimized running on that, plus some Python wrapper around that. But if you want to create a vector, then you can create a vector from a list of lists. So this list of lists only appears when you call this function np.array to create the vector, and then afterwards, if you print that, if you print the vector, but internally, it's the vector is not a list of lists. Internally, it's a completely different object. So we can say type of v, and type of v is not list. Otherwise, type of v would be list, right? But the type of v is numpy.ndarray. So it's a completely new data type that doesn't have anything to do with lists. It's just at the point when we create the vector that because somehow we have to feed the numbers into the creation of the vector, right? And when at the moment when we create the vector, we input a list of lists, and then afterwards the vector gets created, and then afterwards it's a vector. Any more questions for NumPy? Okay, who thinks this is trivial, what we're doing up to now? Okay. Who thinks this is kind of difficult? Okay, then we can go faster. Vectors don't have two elements, they can have any number of elements, right? So we can also have three-dimensional vectors, for example. So we can have a vector, let's create a vector v3, which will be 1, 1, 1, and w3, which will be negative 1, 1, 1. And these both are now vectors in three-dimensional space. So this vector is 1 to the right, 1 up, and 1 to the back. So it will be kind of this, v3. And w3 will be 1 to the left, 1 up, and 1 back. And well, I think our imagination kind of stops at 3 dimensions, at least for me. But a vector can easily have 100 or 200 dimensions, right? And it's still the same thing. It's just a bit more difficult to visualize that. And now, if we multiply this vector by any number, for example, we take some number alpha times v3, plus some different number beta, times W3. Let's say W3 is 1 to the left, 1 up, and 1 back, so it's kind of here. W3. Then, depending on the numbers alpha and beta, I can get different vectors. So I take some alpha times this vector plus some beta times this vector. And can anybody say that all possible combinations of alpha times V3 plus beta times W3, what kind of shape do they take in three-dimensional space? Oh? But it's all possible combinations of V3 times some alpha, they would form a line, right? But I can combine, I can add parts of W3. There will be a plane. It will be a plane, exactly. So it will be a plane like this. It will be a plane in three-dimensional space. And can anybody say which points does this plane go through? Can anybody say, we need 3 points. Can anybody tell me 3 points on this plane? So what we take is, this is what we call linear combinations. So all linear combinations of V3 and W3 in three-dimensional space, which points do they go through? Yes? Yeah, so exactly. Hopefully they go to V3, because if I take alpha to be 1 and beta to be 0, then it will be V3. It will also go to through W3, because if I take alpha to be 0 and beta to be 1, it goes to W3. And if both alpha and beta are 0, then the result will be 0. So this plane, which we call a subspace of R3, goes through V3, W3, and 0. Okay, so if you want to specify a three-dimensional array, I really recommend you to start with the row vector and then transpose it to get a column vector, right? So V3 is np.array 1, 1, 1 dot transpose. So V3 is this, and W3 is np.array negative 1, 1, 1 dot transpose. So W3 is this. And now we take a linear combination of them. So we say 2.3 times V3 plus 1.2 times W3 is this three-dimensional vector, which is on this plane. So this is just some vector on this plane defined by V3 and W3. As a note of caution, maybe we can talk a little bit more about that in future. It's possible to do something like this. V3 is np.array, and then give it not a list of lists, but only one list. Maybe I write don't. V3 don't. This is possible in NumPy, but this is not a mathematical vector. So I recommend you not to do this. So the difference here is that into the method np.array, I only entered a list of numbers, but the result will not be a mathematical vector. If you want a mathematical vector, you should enter a list of the rows. So if it's a row vector, it should be a list of numbers. Who understood this? Okay, yeah. You can do this, but only do this if you're really sure that you know what you're doing, right? As a general rule, I recommend you always to do this. Always use mathematical vectors, because if you use mathematical vectors and you get the dimensions wrong, Python will crash, and it will tell you that the dimensions are wrong. If you use this is called a rank 1 array. Python will not crash, but Python will continue doing some calculations, so you will get some result, and you will not find your bug, and Python will not tell you that your dimensions were wrong. Not a mathematical vector. Okay. Okay. That I think we can probably spend a bit more detail on that. I think there will be something on the exercise sheet. So don't do this. Don't give np.array a list of numbers. Always give it a list of numbers. Okay, now the most basic thing that we would like to do with vectors, well, we now know how to add them, how to multiply them with numbers or scalars, how to subtract them. One thing that would be nice if we could do would be to measure the angle between two vectors. And that's not quite straightforward, but there's some very simple thing to get some combination of the angle and the length of the vectors, and that's called the dot product. Who knows the dot product? Okay, not everybody. Okay, so everybody else should pay attention now, because we will, throughout the rest of this lecture, we will use the dot product a lot. So, dot product. It's actually very simple. So let's take one vector 3, 2 as a row, and one other vector 1, 3 as a column, and let's draw a small dot here. So it's called dot product because we draw as a small dot. And it's actually very simple. So it's this times this plus this times this. So on the left side, you go from left to right. On the right side, you go from top to bottom. And you always multiply the elements, this times this, plus, and then you add them up, this times this. So this is 3 times 1 plus 2 times 3, which is 3 times 1 is 3, plus 6 is 9. And we will use this operation. Who understood this, how you calculate the dot product? Okay. Everybody has to understand how you calculate the dot product, because otherwise you will be lost through the rest of this lecture. Did you have a question, or no? You just understood how the dot product works. Great. So in NumPy, it's very easy to calculate the dot product, and you will do it very often. So I will be a bit lazy, and I will say from NumPy import dot, because I will use the dot product all the time. I don't want to write np dot all the time. I want it to be a bit more convenient. Okay, so I can say dot v transpose and w, which is 9. I think you have to look there. If you pay attention, you will see that in NumPy it's not the number 9, but it's a one-element vector with the single element 9. So actually, in NumPy will do this. If you want to, if you look at this, if you look at the dot product, here you have to be very careful with the dimensions, so the dot product actually works, right? because you want to multiply this with this and this with this, if one of them is longer than the other one, it will not work, right? So this vector on the left, the dimensions are, the number of rows is 1. So you always name the number of rows first. The number of rows is 1, and the number of columns is 2. So it's a 1 by 2 matrix. And here, the number of rows is 2, and the number of columns is 1. So it's a 2 by 1. And in order to be able to calculate the dot product, this number always has to be the same as this number. Right? So if this is not the same number as this number, then Python will crash and the dot product will not be defined. So you have to be careful that these are the same. And then the outer numbers, they define the dimension of the result. So this, the number of rows of the first will be the number of rows of the result. So the result will 1 by, and the number of columns of the second argument will be the number of columns of the result. So the inner numbers always have to be the same, and then the outer numbers define the number of rows and the number of columns of the result for the dot product. You can get the dimensions of the vectors with shape np dot. So you can say v transpose dot shape is so v transpose, which is this one. V was a column vector before, and then I transposed it to become a row vector again. So that should be 1, 2. And w dot shape is 2, 1, right? These are. And in order to be able to calculate the dot product, these numbers have to be the same. Now, if I want to visualize what the dot product does, let me draw the two vectors. So, if this is W and this is V, and I want now to calculate V transpose dot W, so the dot product between V and W, what I do is first I project this vector on this vector. So I draw a line that has a right angle here on this vector. So I project V on W, and the result will be, I think I can call it VP, V projected. But actually I'm not interested in this vector, I'm just interested in how long this is. I'm just interested on how long this is. So this will be the length of V projected. And what I do is I project V on W, I take this length, I take the length of W, and I multiply these. And this is the dot product between V and W. So V dot W is the length of this projection times the length of W. Who understood this? Okay. So you take this vector V, you project it on the vector W. So you draw a line with a right angle. You take this length, you take the length of W, and you multiply both of them. And incidentally, the result is the same as if you do this. This times this plus this times this. It's just the same. Okay, now if we want to calculate how long this is, we have to maybe we know this angle here, theta. And now we have to do a bit of cosine. So there's this, who knows this SOHCAHTOA memory? Okay, so in English there's this thing, SOHCAHTOA, and this is just to memorize sine, cosine, and tangents. So it just says that this part says that sine theta is opposite over hypotenuse, cosine theta is adjacent over hypotenuse, and tangents theta is opposite over adjacent. Because here we have a right triangle, right? We have an angle here, and we have a right triangle here. And here, I hope everybody knows that if we have a right angle here, and this is our angle theta, then this is the hypotenuse. This is just the line that's opposite to this right angle. This is the adjacent because it's adjacent to that angle, and this one is opposite to that angle. Okay, so from this we can recall that cosine theta is adjacent over hypotenuse. So cosine theta is adjacent over hypotenuse. And in our case, the adjacent to that angle is this VP, the length of VP, and the hypotenuse is just the length of, so this is the adjacent and this is the hypotenuse. It's just V. And now I can, if I want this, I just multiply it by this, and I get that the length of this projection is the cosine of the angle times the length of this vector V. And so if this will come, I can plug that in here. If I want to look at this dot product, maybe this will fit in here. So let me just take the definition of the dot product. It's V transpose dot W will be the length of the projection, which is just this. So it's just the cosine of the angle times the length of V times the length of W from here. So the dot product between two vectors, V and W, depends on the cosine of the angle between them and the length of the vector V and the length of the vector W. So it's a combination of measuring the angle between the vectors and the length of the individual vectors. Who could follow this? Oh, okay, so it was not so difficult, I guess. Now from this I can, okay, I think this is important. Now from this I can also calculate the angle by just dividing by this and then taking the inverse cosine of both sides, right? So it's, if you want to have the angle, probably I don't have to do this for you. You can, it's very easy. So if you really want to have this angle theta, then maybe I can do it. So I divide by this part. So then the cosine of the angle between the two vectors is equal to V transpose dot W divided by length of V times length of W. And if I really want to have the angle is the inverse cosine, or the Arcus cosine, of V transpose dot W divided by the length of V. times the length of W. This is just if you want to get the angle between two vectors. And what's nice here is by this, we can now calculate the angle between two 100-dimensional vectors, right? If V is 100-dimensional and W is 100-dimensional, maybe it's not very obvious for us what the angle between them is, but we can easily calculate the angle with this formula. And based on this, we can now also define the length of a vector. Maybe I just clean this. So the trick of defining the length of a vector is just to dot it with itself. So I calculate the dot product between a vector and itself. So the length of a vector. So I just calculate V transpose dot V. So this is by this formula in this red box up there. This is the cosine of the angle V times the length of V times the length of V. What's the angle between V and itself? It's 0. And what's cosine of 0? Cosine of 0 is 1, exactly. So this is just 1 times length of V times length of V, which is just length of V squared. So I can get the length of V, I can get the length of the vector just by dotting it with itself and taking the square root of the result. So let's do that in Python. So let's import math. Import math. And then let's do math dot square root of dot, what is V? Or maybe we should first check what V is. So V is this vector. V transpose dot V. So the length of this vector V is 3.605. And there's a convenience function in NumPy. So this also we call the norm of the vector. So there's a convenience function. There's this package numpy.linalg for linear algebra dot norm of the vector V, which is the same. So this np.linalg.norm just gives you the length of any vector. Any questions so far regarding the dot product? So you will have to use the dot product a lot during the exercises. And you will also have to define vectors. And you always have to take care of this, these dimensions here. Just make sure that the dimensions are always right. If the dimensions are wrong, the dot product is undefined. Yes?
I need to make sure that the first vector is always on its side and the other one always.
Yeah, so to make the dot product defined, here, this number has to be the same as this number. So if you get the shape of the first vector, then the number of columns of the first vector must be the same as the number of rows of the second vector. If not, Python will just crash. It will just tell you that it cannot dot these two vectors. Any more questions so far for vectors? Yes?
What happens when you add two vectors like this, one transpose and the other?
Oh, I don't know. Let's try. V transpose plus W. Oh, okay. So V is this, W is this, and V transpose is this. So when you add them, this is something in Python that's called broadcasting. I think it's not really mathematically defined what happens there. But what Python does, it does its best. So it tries to add them as well as it can. So you have to be a bit careful. This can be sometimes be very convenient. And sometimes I think it can introduce bugs. Therefore, I recommend you to always do something like this. Assert shape V transpose is 2, 1 or so in your code. So you, oops. Oh, so, no, sorry. So V transpose dot shape. Okay, so it's not 2, 1. So I think it's 1, 2. To add a number of assertions in your code, so you don't get any results where NumPy tried to do its best and add some vectors which mathematically don't really add. So you have to be a bit more careful, I think, in NumPy than otherwise. So always check your dimensions. Okay, that was a good introduction because now we see this thing here, which is not it's something else than what we've seen. And this is called a matrix. So what we can do is we can write vectors next to each other. So if we have one vector, 1, 3, 5, and another vector, 2, 4, 6, then we can just write them next to each other in one big thing, and this big thing we call a matrix. So 1, 3, 5, 2, 4, 6. And this is really just the same as a vector, just that we have multiple rows and multiple columns. So the shape of this is 3 by 1, this is also 3 by 1, and this is 3 by 2. And there's multiple ways you can think about matrices. And one way is to think about a matrix by columns. So you can just say that this matrix is just 2 column vectors. But you can also see it as a collection of rows. So you can say that this is 3 row vectors stacked on top of each other. And if you define the matrix, you always have to go by rows, right? As we remember. So if we want to define this matrix, what we have to do is we say A, matrix A is np.array. And now, as always, we just give a list of the rows. So the first row is 1, 2. Then the second row is 3, 4. And the fourth row is 5, 6. And now our matrix is A. So this is just exactly the matrix that we wrote here on the backboard. And now we can also transpose matrices. And it's basically the same as transposing a vector. We just make it, if this is standing up, we make it lie down. So we take the main diagonal and we just flip it along the main diagonal. So that rows become columns and columns become rows. So this transpose is 1, 2, 3, 4, 5, 6. And we can do the same in Python. We can just say A.transpose is just the matrix transposed. Okay, and now we can also calculate the dot product between a matrix and a vector, which is basically the same as calculating the dot product between two vectors. Maybe I want a new blackboard for that. So, what I want to do is I want to calculate matrix dot vector. So let's say I have matrix 1, 2, 3, 4, 5, 6, and I have a vector 2, 1. Can anybody say what's the first thing that I need to check to make sure that this dot product is even defined? Yeah, I need to check the dimensions or the shapes of both. So the shape of this is 3 by 2, and the shape of this is 2 by 1. So is this defined? Can I dot them? Yeah, so because this is the same as this. And the result, what will be the shape of the result? It will be this by this, right? So this will be something, I don't know what it is, but I'm sure that it will be 3 by 1. So it will be this by this, and these are the same. So these are the same. Okay, now there's two ways for thinking how to multiply matrices with vectors, and the first way is to calculate the dot product between all the rows of the matrix with the vector. So I will calculate the dot product of this and this And then I will calculate the dot product of the second row times the vector and the dot product between the third row and the vector. So that's the first way to think about this, which is the dot product with the rows by rows dot product with rows. So the result will be 1 times 2 plus 2 times 1, which is 4. Then the next element, so the first entry of the result will be the dot product of the first row with this column. And the second entry will be the dot product of the second row with this. So it will be 3 times 2 is 6, plus 4 is 10. And the third entry will be 5 times 2 is 10, plus 6 times 1 is 16. So in this way of thinking about it, the dot product of this row times this column gives this entry, and so on. So we can do the same in Python. So we have our matrix A, then we want our vector maybe U. Is np.array, what is it, 2, 1, 2, 1, transpose. Let's just check that it's correct, okay. And now I can calculate dot AU, which is exactly this. So the dot AU is 4, 10, 16, which is exactly our calculation here. And now there's a second way to think about exactly the same calculation. So let me draw the calculation again. So the second way to think about this is as a combination of the columns. Combination of the columns. So we take exactly the same calculation. It's just a different way to think about the same calculation. First column is 1, 3, 5. And the second column is 2, 4, 6. And we multiply this by 2, 1. And the way here to think about it is that the result will be 2 times the first column plus 1 times the second column. So this vector just tells me how much I want of column 1 and how much I want of column 2. So this will be 2 times column 1 plus 1 times column 2. And it's exactly the same calculation. It's just a different way to think about it. So it gives me a weighted sum of the columns of the matrix, where the vector tells me how much I want of the first column and how much I want of the second column. So 2 times column 1, 2 times, this is the same as 2 times 1, 3, 5, plus 1 times 2, 4, 6, which is 2, 6, 10, plus 2, 4, 6, which is 4, 10, 16. So it's exactly the same calculation. It's just a different way to think about the same calculation. Are there any questions so far? Yes?
If you're thinking of doing it in Python terms, then you really need to think in rows, don't you?
No. And I mean, if you define the matrix, you do it in rows. But in Python, you will just, if this is A and this is U, you will always say dot AU, right? And whether you think about it this way or this way, it's your own preference. It's just different ways of thinking about the same calculation. So let's call this here, let's call this A, and this we call U. And so both calculations will be A dot U, or in Python, dot AU. And it's the same calculation as U. So it's A dot U. It's just the way that you think about the calculation is different. Here you think about the calculation as the dot product between the rows and the vector. And here you think about the calculation as calculating a weighted sum of the columns. But the calculation is the same and the result is the same. Okay, and then the last thing that you will need for the exercise sheet is to multiply two matrices. So let's come up with the multiply or dot matrices, or matrix dot matrix. Let's first define two matrices A and B. So A is np dot array 101 is the first row, and then the second row will be 011. And the second matrix will be array 1, 2, 1. And the second row will be 1, 0, 2. Okay. Who thinks that I can dot these two matrices? Maybe I can just print them. A is this, and B is this. Who thinks that I can calculate A dot B? Who thinks that I cannot calculate A dot B? Can anybody give a reason? Yeah? The dimensions are not exactly. The dimensions are not correct. So A dot shape is 2, 3, and B dot shape is also 2, 3. So basically, I have a fat matrix times a fat matrix, and this doesn't work. So A is a fat matrix, and B is also a fat matrix. A and B are both 2 by 3. 2 by 3, and B is also 2 by 3. And this is undefined. So what do I have to do? Can anybody propose something? Yes? I transpose one of them. Maybe I transpose B. I make B from a fat matrix, I make it a skinny matrix. So now it's 3 by 2. So what will be the shape of the result? So now these two numbers are the same, right? So I'm fine. I can calculate that. What will be the shape of the result? Yes? Yeah, it will, exactly. The result, I don't know what it is, but I'm sure that it will be 2 by 2, right? Okay, so let's transpose B. I just say, or maybe I can say A dot A B transpose. And this is the result. So it's a matrix 2, 3, 3, 2. One thing where you might, or you definitely have to be careful, is what if I flip the order? What if I do it the other way around? So now we calculated A dot B transpose. So A was 2 by 3, wasn't it? 2 by 3. B transpose was 3 by 2. And this is equal to some result which was 2 by 2. Maybe I call the result C. What if I now calculate B transpose dot A? Is that the same matrix? Who thinks that I can flip the order and it's the same matrix? Who thinks I can flip the order and it's undefined? This case. Who thinks I can flip the order, it's still defined, but it's a different result? Okay, so let's flip the order. Let's look at the dimensions. So B transpose is 3 by 2. A was 2 by 3. So these numbers are still the same, right? So the result, I can still do it. I can calculate the dot product. And the result will be, maybe I call this D. The result will be 3 by 3. 3 by 3. So it cannot even be the same matrix, right? So you have to be very careful if you calculate the dot product between matrices, the order matters. So it's not commutative. So dot B transpose dot A is this matrix. It's a completely different matrix. It even has completely different dimensions, right? So you cannot just flip the order and hope that everything goes well. Okay, so then let me just show you a simple way to multiply two matrices by hand. So this is just to matrix dot matrix. Let's say we have these two matrices A. I think A was 1, 0, 1, 0, 1, 1. That was A. And then we wanted to calculate the dot product with B transpose. And B transpose is 1, 1, 2, 0, 1, 2. So then I think the most common way that you have probably learned to think about this multiplication is that, let's first check the dimension of the result. So this is 2 by 3, this is 3 by 2, so the 3's match and the result will be 2 by 2. So it will be something that's 2 by 2. And the simplest way to think about this is that this entry here will be, because it's in this entry is in the first row and the first column, so it will be the dot product between the first row of A and the first column of B. So it will be the dot product between this and this. And then this entry, the first row, second column, will be the dot product between the first row of A and the second column of B. Let's just do the calculation. I think we have a few minutes left. So this is, let's start with this entry. This entry, first row, first column, so it's the dot product between the first row of A and the first column of B transpose. So it's 1 times 1 plus 1 times 1, it's 2. Then this entry here, it's in the first row and the second column, so it's the dot product between the first row of A and the second column of B. So it's 1 times 1 plus 0 times 0 plus 1 times 2, which is 3. This entry here, it's in the second row, first column, so it will be the dot product between the second row of A and the first column of B. So it will be 0 times 1 plus 1 times 2 plus 1 times 1 is 3. And this entry here is in the second row, second column, so it will be the dot product between the second row of A and the second column of B transpose. So it will be 0 times 1 plus 1 times 0 plus 1 times 2. It's 2. Oh, it's exactly what we calculated up there. Okay, I think this is everything that you needed for the exercise. I mean, you can also, of course, you can multiply a scalar by a matrix. You can just say, for example, 2.3 times A, which is this matrix. You can dot two matrices. You can dot matrices with vectors. You can dot two vectors. You can add two matrices. You have to take care of the shapes, as we saw. But A was this matrix, and B was this matrix. So you can do simple things. If the shapes match, you can... one thing where you might want to be careful is if you calculate A times B, this is not the same as A dot B. A dot B is not even defined. I think we transposed B. Let's see what Python says. If we calculate the dot product between A and B, it says that shapes 2, 3 and 3, 2 are not aligned, right? So this 3 is not the same as a 2. Can anybody say what's the difference between A times B and A dot B in Python? Can anybody spot what A times B does? Yes?
It's just element-wise multiplication.
Yeah, it just multiplies all the individual elements of the two matrices. So be careful, don't write A times B as you would probably do in MATLAB. Because A times B just multiplies the individual elements, and it's completely different from A dot B, which is the matrix multiplication. That's two very different things. We can add two matrices. Did we do that? No. So we can do, this is defined, A plus B. A minus B, it's also completely fine. A divided by B, this calculates the, I mean, it's element-wise division, where you have to be careful because in B this element here is 0. So here we divide A here is 1 and B here is 0. So this element is 1 divided by 0, which is infinity according to NumPy. You might argue that it should be not a number, but in NumPy it's infinity. You can multiply with numbers. We saw that. 3 times A. It just multiplies, it's just element-wise multiplication. You can divide by numbers. 1 divided by A. Oh, there's a lot of zeros in A. Oh. Maybe 1 divided by B is more interesting. Yeah, I think that's probably everything that you hopefully need for the... You can look at the data type. You can say A.dtype. And this gives you... That tells you that A is a matrix of type integer, so it contains whole numbers with 64 bits, each of them. Okay, are there any remaining questions on NumPy? Yes?
So I could probably make a function that automatically transposes one of the matrices and checks if it's the right shape, if they have the same shape or not.
Yeah, so, I mean, the checking whether the same shape Python does that for you. If you call dot, Python will throw an exception and tell you that the shapes are not aligned. So you don't have to check really for the shapes if you calculate the dot product. Yeah, but in a function you can transpose matrices, you can dot matrices as you like. Yeah. Okay, then have fun with the exercise sheet and see you next week. Thank you.